Hi everyone, my name is Sambhav and I'll talk about a project which is basically involves comparing the original graphs and the perturbed graphs. So NetGraphSim is basically a simulator which is generating uh, original graph with some nodes and the perturbed graph with some nodes where it keeps intact the original nodes, but it has the properties where it will basically create some extra nodes or modified nodes or remove nodes. So here, the solution that I have approached is in the following way. So basically, when NetGraphSim produces the NGS files, we are parsing the NGS files to load the graph, which will basically give us and the details regarding the number of nodes and their edges. So I have used the function netgraph.load to basically parse the NGS file through the help of load method. Then I am basically constructing the objects of nodes and the objects of edges. Now in the NGS file, when we parse it, we get two things, that is the node objects and the edges. Now edges have basically action objects present inside it. So therefore, in order to compare, to basically calculate the similarity between edges of the original nodes and the perturbed nodes, we are calculating a similarity score. So the idea is to create shards first for nodes and for the original nodes and the number of perturbed nodes. And similarly, we have to create shards for the combination of original edges and the number of edges present in perturbed graph, right? The main logic that I thought was to consider all the properties of the nodes along with the edges in order to calculate the similarity score and then identify whether the node or an edge is modified or it is newly added or whether it is removed. I have chosen the similarity metric as the Euclidean distance, where basically we are trying to calculate the Euclidean distance between the node objects. So whenever we are calculating the Euclidean distance, we are actually considering the properties of that complete node object and the properties of the complete edges object, right? So the steps and workflow are here. First, we start with the graph generation where we parse the NGS file, .ngs file to be exact. Then we do the and then we generate the shards here. So for each node that is present in the original graph, we basically calculate the similarity score for the each node that is present in the perturbed graph, and similarly for the edges. As informed earlier that I have used Euclidean distance metric, but also to give equal importance to all the attributes, I have actually normalized all the property values so that equal weightage can be given to all the properties, and not only, and it's not just that one property influences the Euclidean distance. This basically this normalization of the properties will actually help us to uh, deduce more meaningful results between the similarity score. So for after we do the pre-processing thing, that is we generate the shards. I have written a pre-custom. I have written a custom method for it. After we generate the shards, then the the shards are basically passed to the MapReduce jobs. So to perform these tasks, I have three MapReduce jobs. One is the MapReduce that is performing similarity calculation for nodes, and the second MapReduce job is for edges, which is calculating the similarity score for edges, and the third MapReduce basically consume the results of both the MapReduce jobs, and basically it deduces the result whether the node is added or it is removed or it is modified. Similarly, if the edge is added, newly added, or it is removed, or it is modified or unchanged. And then after all these results are collected in from the third map reduce job, we basically compare it with the gold answer, that is the YAML, which is being produced by the NetGraphSim, right? So the project structure is similar, is here where we have the major um, source codes in the source directory in the and in the resources we are producing the outputs. So in the logs directory we are generating the log files. So to run the project, we can do it locally, or we can do it on AWS EMR by deploying our jar there. So let's see while we run it locally first. So this is my main method where actually uh, I am parsing the NGS file, And then so load graph and load generate combinations, load graph and generate combination are the functions here where which will actually parse the ngS file and generate the combinations, that is the shards. And also to normalize the values, I have actually, while parsing the node objects and the edges object, I have actually get their min and max value, so that I use those min and max value to normalize the properties. So in resources right now, I do not have any output folder. So I'll just trigger my main method here from here. So I'll just show the configuration. I have given the program arguments from here where we are passing the location of the input files and the output directories where we want to generate the output. So let's start with the execution of the program. So right now it is basically going with 300 nodes here. So there are 300 nodes in original and there are 291 nodes in perturbed, and we'll see there will be output directories created in resources. So there are some intermediate files created, that is the shards, and then there are some results created from the nodes, that is the scores of the nodes, and there are some results created of the edges, and then by the third map reduce job we are creating the final our final judgments whether the nodes or edges are modified or they are removed or they are unchanged. So here are the logs. So yeah, we can clearly see that 77% is our accuracy which is coming right now. Now these are the output directories that have been produced. So we have output of the nodes. So these are basically the keys mapped with the scores with all the perturbed nodes here. And I have output edges here, which are the edges mapped with the corresponding edges along with the similarity score. And finally, we have the output results. So here we basically have the edges modified or edges removed or edges unchanged or nodes modified, removed, or new nodes added. And then this set we basically compare with the YAML, and we have written another code a script file here, result.scala, which will basically compare with the golden set. So let's now try to execute this jar. I have deployed the jar on my AWS EMR. So we'll try to basically run the jar. But first I'll show my S3 bucket where I have the input here. I have placed all the YAML file and the NGS file. So I was trying multiple combinations here. So it will have the right now I have the NGS file with 300 nodes and original and 291 nodes in perturb. So let's go to the instance here. So I have already ran it. So I'll just run my cluster again. So I'll edit the configurations. I have all the program arguments set here. Everything is fine. I'll just save and I'll clone the cluster. So we'll check. This one is the older one. This is so the job has been triggered and basically it will take around like 3 to 4 minutes to complete. Yeah, meanwhile we can check the jar files here. So I have a jar file. This is the modified jar file which I'll be using. So meanwhile the job runs, we can go through the code flow to understand how exactly the, the program is executing, right? So the control starts from here where I'm invoking the main method. Then I have my parse method. So args0 I'm receiving from the arguments. And this parse method is basically, let's go to it, is basically responsible for parsing the file. So whether I'm invoking my program through the local file system or whether I'm using the S3 bucket for accessing the files. So my parse path is able to handle both the cases. So this will basically return me the directory, the file name, and whether the file is present in the local system or in the remote. So is remote is basically a flag which is helping us to identify whether the file is present in S3 bucket or if it is present in the file system. And similarly, I parse the path for the second argument that I have given the path of the second the NGS file, that is perturb.ngs. So I'll fetch both of the names. Then I'll pass these values to the load graph and generate combination. So this load graph and generate combination is for generating combinations of nodes, and for load graph and generate action combination is for generating the combination of actions. So when this combinations are generated, now what we are checking is we are basically trying to run the map reduce job for nodes. So this is my node similarity score job where I'll invoke the run map reduce score. Now let's come to the part where I am actually invoking the configure function. So my configure function is helping me to parse the attribute ranges file. So let's see the attribute range file here. Attribute range file is the one where I have the attribute ranges of all the properties of my nodes, right? So this attribute range is important for the normalizing thing that is basically helping us to get the more meaningful and precise, more meaningful inferences from the similarity scores, right? So let's move back to this function. So configure is basically the function which runs before the map function. If I go to the map method, so when the configure is executed, we are basically invoking the attribute ranges, which will hold all the range of all the properties that are being considered in calculating the similarity score. Coming to the map part, we are basically parsing the nodes from the combinations that is being generated. So there is combinations.txt, which is basically has all the that is basically a shard which is having all the combinations, right? So and then we'll pass the original attributes and the perturbed attributes to the calculate sim score, where basically if we traverse to the similarity score function, we are actually calculating the differences, and then these differences are passed to the Euclidean distance calculation, where we are uh, doing the square of those differences, then sum and then square root, right? So, and for the similarity score, we have calculated. So basically, the shorter the Euclidean distance, the more similar the node is. That is how it is being interpreted here. So the similarity score is calculated then, and post that, when the key and value pairs are emitted, we move on to the reducer method, where basically we are sorting on the basis of higher similarity score. So we have sorted in the descending order. So that is how the flow works. So first the configure method is called, then the map method is called, and then the reduce method is called. Let's just check if my job is completed. Yeah, I think it's completed. So now let's check our S3 bucket. I think our outputs have been created. So we have output nodes. Then we have, so output results, right? So we'll have values here. So if we open this, we'd be able to download it. So yeah, this is the file exactly. We'll download it and then we'll open it. So yeah, we have for 300 nodes all the edges modified, edges unchanged, edges removed, nodes modified, nodes removed, nodes unchanged, new edges added, and new nodes added. So we have generated all the possible combinations that our algorithm has detected, and these combinations are then compared with the golden set, which will basically help in generating the ATL, all the parameters related to ATL, ATL, that is battery traceability link. Uh, and post that, we are actually calculating the accuracy, which is coming to be around 77% for this case. Thank you.